Hello and good afternoon today. I'll be continuing with my series of videos on data structures and their implementation in C. If you're around, say hello in the chat, and I think we're going to jump straight in today. So if you remember on the last video, the last thing we spoke about is the big O notation, and it is something I'd like to focus on a little bit again. So let's have a look at what I had drawn there, which is the following thing, right? Where did my pens go today? Okay, so what we had is our single linked list, which is slightly out of focus. Let me go see if I can fix that. There we go. It's our single linked list where we had our head and tail items, which are called fail if you remember, and our three data elements. And we covered that removing the head of the list would be one operation, because we could find it immediately and then reset the pointers so that we can just remove it. Whereas removing the last element, we had to move through all of the items to be able to do that. Now, if you don't remember what the ideas behind this was, the previous video should explain all of that. But it meant that removing the head had a big O notation of 1, because it took one operation to do these things. And then removing the tail took an operation of ON, which is the amount of elements that are part of our set, right? So we had 3 elements in here, the Bluey, Sunny, and Woody elephants. And then in order to do this operation, we needed to do that many steps to be able to remove that pointer. So that's what the big O notation does. And of course, similarly, having to step through the arrays to show every element one by one, of course, we also had to go element by element. So that is again ON. That is pretty normal for a list, as you'd expect. If you want to list all the elements, you need to loop through the whole list. Now, there's one thing that we didn't really mention, which is finding the elements either. So if we want to find the elephant or the element, for example, that has Sunny in it, then we'd still have to walk through this whole list. And although we'd find it at a second element, because we don't know up front where this is going to be in, at most we're going to have to walk through the whole list, which is the n elements. So hence, finding an element, which I didn't draw here, would also be an ON notation. Okay, so that's the situation that we ended up with. But now, what we're going to have a look at is to see whether we can improve one of these operations, which is the removing of the tail, so removing the last element. But in order, before we start actually going there, we need to have a look at our code. Now, in between the previous video and the current one, I've changed the name of the file. So if you remember, it used to be array.c, but we've changed it to lllist.c. But let's open this file and see what's in there. Oh, if I typed that correctly. Right, so we had plenty of things in here, right? So we had the main body of our file here, where we created 3 elephants with the names Bluey, Sunny, and Woody to make them blue, yellow, and brown, like we have here on the screen. We created our list in this line. We added our 3 elements to the list, and then we did some testing to see whether our code worked. And then we walked through the list to list our elephants. So that's what it is. Now let me remove these again, because I just want to show you walking through the list again. So if we did gcc without tests, we do lllist.c, and then run it, we get our 3 elephants. That's what we still had. So that was great. But as you see, that all of our code is currently in the same file, which makes things quite tricky to do. So we have the bits about the elephant in here, so the elephant constructor and show elephant info. We have things about creating the list in here, and that of course gets all very messy. So it'd be a great idea to split it out first before we continue. So in order to do it, we're going to split every single element into its own file. So first of all, let's do the elephant itself. So we're creating a file, elephant.c. So in this C file, we're going to put in all the functions, or all the methods, depending on how you want to call that, that make up the operations that do the elephant. So I just copied them from here, pasted them here. But there's one thing that we do need to think about still, is that the elephant structure is still going to be used as well, right? It needs to be shared between multiple files. And in order to do that in C, you create an H file for that. In this case, elephant.h, where we then put our struct in. So remove that over, put it in here. Now, when we have this, then of course we need to tell the main file, the llist file here, that we also need to include this definition. And you see already that there are two different things that I'm doing here with the include. So the pointy brackets are the ones for the standard C libraries, and the one with the double quotes are the ones from the local project. And for those, the include directories is going to be important in case we want to store those in a different file. Now, of course, if we compile this llist file, we're getting quite a lot of errors, right? Because it doesn't know what all those functions are anymore. So to make sure that these functions for all the elephants are also known, we need to create their the prototypes need to be available in the C file. So I'm going to have to copy these here. Add a semicolon to the end, because we're not going to include the body. It is just going to be the definition. So we call it the declaration. And I'm basically just copying and pasting these. This is our function that does the list elements. And then we have the show elephant info that shows the elephant info. So those are our 4 functions. So we've now put them in a header file. Now if we compile, we're still getting some errors, right? Although we have, of course, defined them, what you see here is, of course, we still only compile one file. We only compared our llist file. So we do need to add that here on the command line to also compile our elephant file. And now we still get a bunch of errors. Now, why is this? Let's have a look at what they're actually saying. It says that here on this line that some of the allocation methods that we're doing, although we have included those definitions here, we haven't done that for the elephant.c file. So we need to do that too. And as a matter of fact, because we haven't included the definitions yet for the struct elephant, we need to move that in here too. So pretty much I've copied all those 4 header files now, the definitions. That doesn't mean they're not all needed, but there's no quick trick on that. Okay, so if I compile them now with both of the files, it compiles again, and when we run the tests, it works again. Yay, success. Now there is a common thing to do for header files, is always ask a guard clause around it. And that is, a way to make sure that it is safe to include the same header file twice without the definitions being created. And this is something that is just a very common thing to do. Sorry, I call it elephant.t, but what I meant to do is elephant.h. It is basically a way to guarantee that if our define isn't defined yet, we do define and define all the elements for the elephant. And if not, then we're just going to ignore it. So that's a very common thing to make sure that you can safely include the same header file without the definitions being copied in twice, because if you would do that, you'd get an error for getting to define them more than one time. So of course, if you compile that, there is no difference still here. So we have done that. So we put the elephant in their own file, but what we really need to do is also do the elements for the list, right? Now, in order to do that, I'm actually going to rename the list file, because this is going to be our, or rather, what's probably easier to do is put our main file into main, and then we purpose the list.c file into the elements for the list, and also extract the methods or the function names into its own h file. Yep. I apparently don't know what to do, so we write that to main. So now it's written everything to main, which is not what we want. So let me open these two files again, and from the list we remove main, and then from the main file we remove everything not main, and that's already done. So, but we know that we're going to have to use the elephant definition in here, as well as the defines for the linked list itself. So we include this here. Now this main body itself doesn't create any other allocations, so we don't really have to implement any, we don't have to include any other standard header files because they're not being used here. Now when we open the list file, where we have our basically our list elements and list data structures, we will also have to split out these structures into their own header file. So we do that with list elements, which defines each element in the list. We have those type defs and then the list structure, because those callbacks are going to be used in other files. So those are the definition files that we need. But of course, we also need to export the some of the functions. Now we don't need to export all of the functions, because what we don't need to define is the elements for creating list elements themselves, because those are being done inside the implementation of list.c. So we don't have to copy this list element ctor and list element detour, because we never call those, we never have to call these things. And because of that, it makes sense to actually define them as static, so that they can't even be called outside this function, because they're only going to be used in here. And similarly, our list element is also never used outside here. Is never used directly by our code. So we are going to have to change this a little bit as well in a moment, because we don't really want to export things being usable by other functions if there are internal things. So we don't want to export basically implementation details. We add again our guard here, which is list.h, define list.h, and then at the end we do the endif, and it is common to use a comment to show what you're actually ending with an intf, especially because there's so many extra lines of codes in between. Now, what we do need to, of course, export is the functions that do the operations on the list. So that is creating a list, the list ctor, that is the detour, destroying the list, that is the function for walking through the list with our callback function, that is the element to add things to our list. I'd like those to have those beforehand. Then we have remove head and remove tail, and that should be it. So now we have those defined in the list. We need to make sure that we actually include our file. Again, we don't have to do anything with the elephant here, because that is an implementation detail for our program and not something that we need to do in our list. The list doesn't know about the elephant type, so we only have to include list.h. When we look at our main script, or sorry, main program, we already correctly include elephant.h and list.h. And if we look at the elephant.c file, we only include elephant.h and not lists.h because we don't need it. Now let's compile this again. Of course, now we also need to specify main, and this cleanly compiles again. And when we run tests, then if I type this correctly, then we get our correct list. And now that means that we have decoupled pretty much everything. In main.c we don't include the any of the functions for the elephant or the list. We have split this out. The list does not know anything about the elephants anymore, and the elephant doesn't know anything about the lists anymore. So the only annoying thing that we have here is that this list element structure type is still being exported, and we don't really want to do that. Now the issue is that the list element is luckily also is used here, so we can't really remove it from here, because that would mean that including the list.h file doesn't work, so because you don't have this list element anymore. So we can't really do anything with that right now, although there are tricks for doing that. Now, we now have, of course, multiple files, so let's add those to Git, and then you get to follow along later with these. So we do need to git elephant.c, elephant.h, list.c, list.h, list.h, and main.c. Of course, I need to add them, not elephant them. So there we go. So we've done that. What I also will do is create a git ignore file to make sure that we don't actually end up committing our test file. We're going to git status. This all looks fine. Okay, we probably should also add the .swp files in here, or it's actually probably better to do that in the upper directory. Yeah. But let's do that in here for now. So we don't really want any swap files that Vim creates either. Status. So there we go. And do the git add .git ignore git status. Oh, I can't type. That's fine. And then we say as a command, split up our code into elements. Okay, so that's the first thing that we've done. We've now very nicely split this up into its own files. That makes it a little bit easier to use. But as I indicated in the start of this video, is that our list still has the issues that if we want to remove the till element, is that we had to move through the whole list. So let's get back to the drawing here. So the drawing here shows all the elements going forward, right? So we have our head element and our tail element, and then we have an element for each of the three elephants. Now I'm going to redraw this in a new drawing, because what I want to do is I want to add an extra element so that we can walk both directions into the list. So let me get rid of this and add a fresh sheet of paper so that we can redraw this. So the first thing we had, and that is going to stay here, is our list itself with our head pointer and our tail pointer. So that's not changing. We also still have our three elephants here. Let me draw these. So we had Sunny, Bluey, and Woolly. And if you remember, we had to give those addresses so that we can keep track of those. So there are 0x101, 0x, oh, sorry, let's make it 1010 and x. It's not often common that these end in ones because they're going to have to be aligned in memory, a subject for some other talk maybe. So we have these addresses, and then we have those corresponding array elements, or the list elements here. Let me draw these out. And these have addresses too. Going 300, 310, and 320. And we remember that each of those list elements pointed to the elephants by pointer. So these pointers are called our data pointer, which we put in the middle element here, and you'll see in a moment why. And then we can point those to the right addresses. So this is 0x1, 0x20, and 0x130. And that is pretty much these pointers that point here. So far, nothing new. And then, of course, we also had our head pointer and our tail pointer that pointed to the right elements as well. So the head pointed to the first one, and the tail pointed to the last one. And then, of course, each of the elements itself also points to the next one, which is our next pointer. And the next pointer for this one is going to be 310, because that is this address. The next pointer of this one was going to be, because it points in this one, and this one is empty because it didn't point or anything. And as I mentioned before, if it's a null pointer, don't fill it in. We can draw the errors for these as well. So that is our single linked list. And to get to the first element, we can easily remove that. But we couldn't remove the last element because there was no way to get from the last element to the previous elements to update the pointers to set these. But that is easy to fix, and that is easy to fix by not only having a next pointer, but also by having a previous pointer. I'll fill these names in here. And then the previous pointers we can also fill in with the address of the previous list element. So this is going to be then 310 and 300. So now if you look at the second element, Bluey in this case, it has a data pointer that points to our data element. It has a previous pointer that points to the previous element, and it has a next pointer that points to the next one. We have a tail pointer, a head pointer and a tail pointer that point to the beginning and end. And this pretty much means that we now have changed our single linked list to a double linked list. And of course, we can draw that on paper quite nicely, but of course we also need to make the implementation for that. So let's give that a go. Alright, so on our left hand side we have our code here, where you see the list element itself, which has our head pointer that I've just drawn, and the tail pointer. Now the list element itself, we already had the data pointer. We have this next pointer. But what I'm now going to add is the previous pointer. Okay, and of course just adding the pointer doesn't do anything, because if we compile this, GCC, then, well, it doesn't throw any errors, which is of course expected because we haven't changed anything. Now, it gets a bit boring to have to type out this whole GCC list all the time, of course. So it is a common thing to create a Makefile for this. So let me just create one. A Makefile is a very common way to do things. If your build system gets more complicated, you do more than this. But in pretty much, in the simplest way, it's pretty much doing this. So we need elephant.c, which we can call O. No. And that's what it depends on, and then we can compile that by doing actually I'm just doing this the cheeky way. I mean, there are much nicer way of doing it, but I just want to have a simple shortcut, and I don't want to explain all of make, because we'd be here for days. In any case, now we have done this, if I type make now, it doesn't do anything because it's already seen that our test file is done. If I type make now, it compiles it. If I type make again, nothing has to be done because it keeps tracks over what needs to be compiled or not. So instead of typing out my whole long GCC list all the time, I can now just type make and be done with it. Which is a nice shortcut here. Anyway, as I said, just adding our definition of the pointer doesn't do anything. We need to actually have a look at all our different operations to update. All right, so the first one that we need to have a look at is our list constructor. Again, we don't really have to do anything here, right? Because we already have a head and tail pointer, so there's nothing here. But what we do need to do something about is to change our list element constructor, because we need to make sure that we set that to null as well. And I'm going to reorder this so that it follows the definition in the file itself. That doesn't particularly matter. So that is again a simple way of doing it. So creating the list is simple, and creating a detour is simple as well. Now the thing is that when we add a list element is where we need to do the extra magic. Now if the so if we add an element to the list and it's our first element, what we do is we create our list element structure, and remember that's the ones here. So that is what list element ctor does, that we have on the line here. And if the head pointer of the list is null, meaning there's no elements, then we can basically set head is E and tail is E, because there's nothing else there. But if there is an element already, then we need to do a little bit more work. So previously what we did is that from the tail element, that is the original tail, to add an element to this, we say that the next element of our original tail is the new element, and then we reset the tail in the next line to the next element. But we need to do a little bit more here, because we also need to update the previous pointer now as well, if we can do that. Now the previous pointer of the new tail is going to be, again, this is tricky to explain, so let me just go draw this out again in a simpler way to make sure that we don't get confused here. So this is our full list, but I'm going to redraw this with just one element here. So bear with me for a second. So we have our main list here. Make sure to get into the screen here. This won't take us long, head, because we only have one element to start with. We have our element here. Bluey, and I forgot which address it had, but let's give it 1010. We had our element here, our list element structure with our previous pointer, data pointer, and our next pointer. Sorry, my handwriting is getting worse. 300 and the tail is going to be the same, because the head points here and the tail points here, the data points there. And that's the situation if we have one element, right? So what do we need to update to create a second element? Well, first of all, we create our list element. That's the simple way. If you look at the code, that's what this line here does. Then, when we do that, we also already set our new data pointer. So we'll just create Sunny here. Zero x 1020, and we can do this. This is nothing trivial or nothing hard about this. But now we need to update our pointers themselves, right? So what are the steps that we need to do? Well, in the original tail, which is this one here, we need to set next to the following elements. So step 1, update the original tail next. So that is the tail. Next, we need to point to the new element. So we put us in 0, 1, 3, 0, and that creates this connection. What we also need to do is that in the new element, we need to set the previous pointer to what the previous tail was. So to write that down is we have the new element E, previous pointer, we need to point to the original tail pointer. So that's list tail. And that then fills in this pointer. And once we have done that, we can then update the tail pointer of the list. Like this. So those are the 3 steps that we need to, and that is one more step than we previously had, because we didn't have to, sorry, I should draw on that pointer as well to be precise, to put that one in as well. So if you go back to the code here, you can see here that we did the first step, we set the tail, or the original tails next to the new element, and then what we need to do next is set the previous element of the new element to what the original tail was. And the order is sometimes, of course, important, because if we would do this line before this one, then we'd already created the tail, right? Okay, so should this be everything? Well, let's have a look. So let's compile this, and I get an error because I mistyped something. It said temp pref equals null, that needs to be pref. Typos happen, and now it compiles again, and now when we run this, well, you get no errors whatsoever because we didn't really do anything with this tail pointer. But let's have a look at what actually the situation is once we add our element. And let's create a GCC session with that, and we set a breakpoint on this line 19 where we walk through the list, just to see how our elements look like. We call GDB with our test file. We set our breakpoint in main.c line 19. Yes, we do run, and then it doesn't do anything. So the reason what I haven't done yet in our Makefile is, although we set it to compile, we didn't add the debugging information. So let's add that back in again. I just simply forgotten about it. Still no debugging symbols. Oh. Because sometimes that doesn't work. Need to compile it again, of course, otherwise the trick doesn't work. Now it doesn't warn about not having these debugging symbols anymore. Okay, so it stopped at this breakpoint here. We type run, and then it stops at our list walk sign, which is what we would expect. Alright, sorry for that. I'm getting a call that I actually really need to answer, but of course that interrupted the stream, and I use my phone camera to do this thing, and I'm also totally out of the flow. So where we were is that we were having we run our program and our list is here. If we now show the lists, let's print the elephants. Oh, why didn't that work? Okay, let's print the elephant. So that is our normal list here. And our list well, has a head and a tail, and it has 3 elements in there, right? We have the 3E0, and then there's the 400s. Pretty sure. Let's see what they say. So it says data next. That is fine. Let's see what it says there. It has no previous pointer to the first element. That makes sense. Here the previous pointer is fine. The next pointer is fine. And then it should be fine for the last one as well. So all the previous pointers are fine. And the next pointers are fine. So there we go. So our list looks fine now. But we do need to do, of course, something for removing elements from the list as well, which we haven't done yet. Because we need to update the pointers there. And if we just remove one element, then we cannot easily do that. Alright, so let's see what we need to do to remove the head element from our list. So we have the remove head on the left side, and then yeah, we need to remove that. Okay, so back to the drawing. I've actually forgot to update this pointer in the drawing. And of course, actually, we have 3 elements already. So that is this drawing. So there we go. So this is the situation where we currently are. Now, what do we need to do when we remove the head? Well, as you can see here in the code, what we do here is that we remember what the next element is in the list, and that can be empty. We call the destructor on our date element, and then we call the destructor on our list element, and then we update the head pointer to point to next. So that's removing the head, right? So what we do here is we look at this element, when I say next, so head points to the first one, we remember what next is, in this case 310, we get rid of it, and then we set the hex, the head to the next element that we've just remembered. That's fine, but when we have a double linked list, we also need to update this pointer, right? This pointer needs to be gone, so we need to set not the head, but the next element in the list. If there is one, we need to set the previous pointer to null. So that is the extra step that we need to do. So let me go back to the code and update our information there. So we remember what next is. We need to make sure that we set the next element, previous pointer, but it doesn't have to be one. So we need to make sure that we check for that first. If there is a next element, then from the next element we set the previous one to our current head. Once we've done that, we can delete the head element, call the destructor on it, then remove the element, and then update the head to next, and then that works. So now the extra step that we had to do is update the previous pointer in head, which is great. Now we have done that, so that is all good. Let's see if this compiles again. So let me quit, yes. We compile again and run our test script, and that still works. of course it still works because we actually haven't removed any elements. So what happens if we move, for example, the head, remove head, and then we just walk through it twice to see the previous one and the next one. Call make. Nope. Because I mistype. Instead of remote head, it should be remove head. Clear the screen. Nope. Clear the screen as and then we run our element again. And now we get indeed what we would expect, right? We get the first time the list it prints bluey, sunny, woolly, and then the second time it prints sunny and woolly. Now let's check with Valgrind to make sure that we don't get any errors. Nope, we don't get any errors, so that's fine. So let me do this once more to remove one more element from the list to make sure that we don't have any bugs. So yeah, in this case you can see that only woolly brown is left. If we do this once more, then the last element should also be gone and it shows nothing. And if we call remove element head once more, then it doesn't create any errors either. So that's all great. So that is removing the head. But what we can also do is removing the tail, and previously that was quite a difficult operation, right? We had to walk through all of these things and do quite a lot of things. But that's no longer necessary. We don't have to loop through this list anymore because we have direct access to the tail element and its previous element. So pretty much removing the tail is the opposite of removing the head. So let's put them next to each other. So we have remove head here, and remove tail should be the exact opposite. So we need to make sure that the tail is not null. We set our pointer to tail, we set our previous, nope, sorry. I need to read, not copy. So we set our previous element to the tail's previous element, and as you remember that can be null. And just get rid of this. So if the tail's previous, only if it is set, we can set the tail previous next to our tail. So I'm very much just mirroring exactly what happens in the removal of the head. We call our, sorry, I need to say tail here, data. Destruct our elements, and we can send set L tail to previous. And now we don't have to loop through the whole list anymore. Now just to make sure that this actually works, let's open up our main again, put it on the other side. So instead of remove head, we can remove tail, compile the code by calling make, running the code. Oh, I've done something wrong here. Lots of things wrong here. Okay, so what is wrong? Well, it still printed the previous items, and then also the first two because we're removing the tail, but then we're getting an error. It says an invalid read of size 8. And as you remember, that is a pointer. So let's pause directly before the removal of the tail and see what we're doing wrong. Oh, what line was that at? That was line 21. Oh, not a function, a line. We call run. We know that our list looks right, but now let's see what happens when we remove the tail. So we're going to step into this. Let's do a print of our list. Print our list. It says our head is the 3E0 again. The tail is 420, fine, and the detour is our pointer. So that's fine. So let's see what our code does now. It set the previous to the tail's previous pointer. So what was our previous tail's pointer? It is the address that ends in 400, which is our second element. And of course, this element itself doesn't have a next element, so that's fine. So there's nothing wrong with this. So we do next. So that means that previous now should point to our 400 address, which is what it does. Excellent. Shouldn't really be a void pointer actually. It should be a list element pointer, right? Oh, struct list element. Luckily from GDB you can just type make, which makes this handy. So let's do the exact steps. If we now do pref, we get, let me put it at the top of the screen, we get our elements in there. So this is fine, right? This is our second element, the previous one points to the first one, and the next points to the third one. There's nothing wrong with that. So what is our next step? We set the tail's previous one, is the element that we're pointing at, the next one to the original tail. That's not right. Did I not copy these things correctly? Okay, no, this should be right. So the next element of the one before the tail, we set to our new tail. No, that's not right. It should point to what our... it should point to null, right? It should point to null because we are removing the element. And there is no next element beyond the end of the tail. Okay, so I think that was what the bug was. So call valgrind, and then indeed everything works again. So yes, you can't always exactly mirror what you're doing. Let's see what happens if we do wrong commands. If we remove two elements, I went to run valgrind. So that still works if we remove all three. That doesn't go right yet. Okay, so we need to check one more thing. What happens if we remove the last element? So let's run GDB again. We do break, and we do that now on line 23. We run, and let's inspect our list first. It's a normal list. We should have the head and the tail both point to the same address because there's only one element left, so that's what we would expect. So let's step into our function. Well, we still have a tail, so that's fine. What is previous? Well, the previous element should be null. So that's fine. So we're not touching this, right? Because L till pref is also pref. So actually, what I could have done, instead of doing this twice, I could do this to make it more concise, because that should point to the same thing. So that's fine. We skip over that. We destroy our till data. That should be fine still. Need to put a point on the right side. That's still data, that's fine. List element we can destroy now, and now we set we can't really set the tail to previous, couldn't we? No, so the tail should still be fine. So there's no problem doing that here. So we set tail to previous to, even though previous, as you can see, is null, which is fine. So we do tail to previous, and then we're done. So that's next. But how does our list look now? See, this is what the problem is, right? The head of the list still points to something and we haven't updated that because we've just removed the last element. So what we really need to do is that if the tail is empty, we also need to set our head to empty. And then we should no longer have the problem. So we use negative if tail is empty, then we also set head to null. Just to clear out that last pointer. Now when we run this, quit the debugger, let's say make, and then when we run valgrind, we have no errors whatsoever. And now what we ended up having done is we have changed our implementation of our list from a single one to a double one, so that our remove head function was already one operation, but the remove tail is now also no longer on, but it is now o1. So by updating our data structure, we actually have improved the performance of our algorithm, but we have added extra complexity and we needed to store extra information in the form of our previous pointer. And this is always something that you're going to have to realize anytime you're writing an algorithm, is that you can make things work better, but there's going to be overhead, and this trade-off is always going to be there. Now I'm going to end here because we've going on for nearly an hour now and I've been interrupted, so I'm really out of my flow. But yeah, we have converted our single linked list to a double linked list, and then next week we're going to have a look at how do we find elements in our list and take it from there again. So thank you very much, and I'll be back next week.